Okay, so as hinted already, the right way to think about this problem with negative weights on the edges is to think about walks, right? So let me remind you, a path is just a sequence of vertices in the graph connected by edges such that no vertex is visited more than twice. A walk, on the other hand, you're allowed to visit a vertex more than once, right? And it would be convenient to think about walks because the nice thing about walks is that you don't have to remember how you arrived to where you are, right? It's a memoryless process, and that would make the dynamic program that we will use to solve the problem, it would make it work out. So that's the main reason to do it. And as before, we will define the distance as minus infinity if there is a walk with negative cycle between two vertices. And otherwise, we will define the distance between two vertices, the shortest walk between those two vertices, because if it doesn't have any negative cycle, the shortest walk, then it will be finite and it would have at most n-1 edges because it can visit only n vertices, so it can have at most n-1 edges. Okay, and as I said, we will see it later on, thinking about it as shortest walk instead of shortest path makes things easier. So here's the official problem. I have a graph. There are weights on the edges. They might be negative. Given two vertices, is there a negative cycle reachable from S? Given a vertex S, either find the negative cycle or find the shortest path distance for S, all the reachable vertices that it can reach. And the third problem that would be of interest is, given a directed graph with weights on the edges, decide if there is a negative cycle somewhere hiding. Okay. Now, this deals with the undirected case, right? Now, usually the undirected case for shortest path in the usual setting, it's not a big deal, right? If we have an edge of length 6, then to turn it into the directed case, all we did was to take the two vertices, let's say U and V, and we put two directed edges between them, one in one direction and the other in the other direction, right? So it's no problem if it's positive. But if it's negative, then we replace it by two edges of price minus 6, but we just created the negative cycle that was not in the original undirected graph. And that kills everything. So in fact, to solve the shortest path problem, shortest walk problem in undirected graph, it's a significantly more difficult problem. You need to compute something called T-joins, which you compute by computing minimum weight matchings. And it's quite complicated. It's way past 473, which is the follow-up course for that. It's something that you can learn if you take a course about combinatorial optimization. So this problem is really difficult, the undirected version. This is it.